yeah, it's a pleasure for me to speak in this seminar. And what I will report on is joint work with Rosie Laking and Francesco Sentieri, both from Verona. And yeah, so let me start first with some notation, usual notation, just to set this, to fix the setup. So A will denote a finite dimensional algebra, although many of the things I will say hold for Artinian rings. And big mod A will be the category of all modules, and small mod A the category of finite dimensional modules. Then int A will denote the set of isomorphism classes of indecomposable injectives. dA will be the unbounded derived category of the big module category. And here we will consider the compact objects. And yeah, it's known that these are the perfect complexes. So the complexes that are quasi-isomorphic to bounded complexes of finitely generated projective modules. Okay, so now let me start with an introduction. So what do I want to present today? So let me start by recalling two important measures. In representation theory, we are interested in the complexity of the category of finite dimensional modules, and there are two important measures that we can use for it. And one is given by the lattice of all torsion pairs. So recall that two subcategories, TF, in mod A, let me write it like this, TF in mod A form a torsion pair TF if we have two properties. First of all, there are no maps from T to F. And secondly, every object, every module has a canonical decomposition in some sense as by a sequence of this form. There is a short exact sequence where M is the middle term of a module in T with quotient in F. Okay, and now we can, if we take the torsion pairs in the category mod A, we can order them by inclusion of the torsion classes. So we set the torsion pair TF to be smaller equal than the torsion pair T prime F prime if T is contained in T prime. And in this way, it is known that we get a pose set and we get, in fact, a complete lattice. Which is usually denoted by tors A. Okay, so that's the first thing. The second thing are the bricks. So a module, again, I recall a notion, a module B in small mod A is called a brick, or sometimes it's called a Schur representation, if its endomorphism ring is a skew field. So in particular, it is indecomposable, but it's a special class of indecomposable modules. And we denote by brick A the collection of isoclasses of bricks. So these are the bricks in mod A up to isomorphism. Yeah, so I said that these are two important measures, and in fact, they are related to each other. It's known, for example, that one is finite if and only if so is the other. And in that case, we have a class of algebras called tau tilting finite or brick finite, which led to a new perspective on representation type. And in fact, there are a lot of brick analogs of classical results on representation type, like the first Brouwer-Thrall conjecture, or the fact that infinite representation type is the same as asking that there is an infinite dimensional module. Also, this has a brick analog, and there is ongoing research on a brick analog of the Brouwer-Thrall of the second Brouwer-Thrall conjecture. And so an important tool for these results and for studying also the interrelationship between these two measures is provided by silting theory. Namely, there are important bijections. The first one is in work of Adachi, Yama, and Reiten. And it is a bijection between the poset formed by the functorially finite torsion pairs and the poset formed by the basic two-term silting complexes in the derived category. And again, here I'm taking isoclasses. And let me stress that these are compact objects by definition. So there is a bijection between these objects, and again, a further bijection with certain pairs called support tau tilting pairs. So here, basic support tau tilting pairs, and these are pairs MP formed by a so-called tau rigid module and a projective module. And again, here I'm taking isoclasses. Okay, and this so-called tau rigid modules, I'm not going in too many details here because this is not so important for what I'm going to say, but these tau rigid modules, they also provide a connection with bricks, because if we look at the set of isomorphism classes of indecomposable tau rigid modules, which is usually denoted in this way, this is in bijection with the set of certain bricks, namely those bricks called left finite, which generate functorially finite torsion pairs. Okay, so we see that we have this finiteness condition here. So we are looking at certain torsion classes, only the functorially finite ones, and here also at certain bricks. And this functorial finiteness, this is a finiteness condition. It's stated in terms of the existence of certain approximations. And it is a strong restriction, in fact. So when the algebra is brick finite, then we know that these are all torsion classes and that these are all bricks. But in general, these are only a special class of torsion classes or bricks. And it turns out that this is for many purposes. For example, if you want to study invariants of an algebra, such as the space of stability conditions or the wall and chamber structure, or the complexity of varieties of representations, then you really need to look at the whole lattice of all torsion pairs and at the whole collection of bricks. And so my aim today is, and I forgot to put the reference. So the first statement one is Adachi, Yama, right? And the second one is Demoni, Yama. and Hasso. So now I would like to remove these finiteness conditions, and my aim is to present you the following result, which is joint work, as I said, with Rosie Laking and Francesco Sentieri. So now what we want to use is still silting theory, but we have to remove this finiteness condition. We don't want compactness. We want to work with large silting complexes. But the problem there is that large silting complexes don't have indecomposable decompositions in general. So we can't reduce problems to indecomposable objects. And to partially solve this issue, we can move to the dual notion of a co-silting complex, because there one knows that this is a pure injective object in the derived category, and then one still doesn't have an indecomposable decomposition for pure injective objects, but one can reduce many problems to indecomposable pure injective objects, and one can work in a topological space which is called the Ziegler spectrum. So I'm going to explain these things in a moment. First, let me state the result I want to present. So it will be a bijection between all torsion classes, and here we will have the equivalence classes of two-term co-silting complexes. So up to an equivalence relation that I will explain. And here we will have an analog of the support tau tilting pairs, which we call co-silting pairs. And these are pairs Zi formed by two sets. This Z will be a subset of the Ziegler spectrum of A, and I will be a set of indecomposable injectives. And so we will have bijections between these sets. And the second statement, so this first statement generalizes the first bijection I was giving here. And now for the second bijection, we have here the whole collection of bricks is in bijection with something which now looks a bit mysterious, which I denote like this, rigid CMI of A. And it will be a sort of large counterpart of the indecomposable tau minus rigid objects, because we are working now with the dual notions. Okay, so I hope that in the next 40 minutes or 35 minutes that I have, I will be able to clarify what I wrote here. So let me start with the Ziegler spectrum. What is the Ziegler spectrum? So first of all, I have to explain what is a pure injective object, and we will work in parallel in the module category and in the derived category. So for the moment, look only at the white part. So a short exact sequence in the module category is said to be pure exact if it stays exact under the covariant Hom functor given by an arbitrary finitely presented, finitely generated module. Okay, so it's mapped to a short exact sequence of abelian groups. And in parallel, we have the same notion in the derived category. So here we start with a triangle, and we say that a triangle is pure exact if, same thing, it stays exact under, or it becomes a short exact sequence of abelian groups whenever I apply the covariant Hom functor given now by a compact object. So it's the analog where instead of looking at finitely presented modules, we look at compact complexes. So that's the notion of a pure exact sequence, and then a pure exact triangle. And then we say that this morphism here, it's a pure monomorphism, and X is a pure subobject, and Z is a pure quotient of the object Y. Okay, so now with this terminology, we can introduce what a definable category is. It is a subcategory of the module category or of the derived category, depending on the context, which enjoys some closure properties. Namely, it's closed under direct products, under pure subobjects, and under pure quotients. Okay, and then we say that an object is pure injective, again, both in the module category or in the derived category, depending where we are, is pure injective if every pure monomorphism starting in this object splits. Okay, so it's a relative injectivity relative to this notion of purity, of pure monomorphisms. And then with these notions, we can form two topological spaces, namely one, which is the Ziegler spectrum of the module category. And the points here are the isomorphism classes of indecomposable pure injective modules. And the closed sets are formed by the indecomposable pure injectives contained in a definable subcategory. And the Ziegler spectrum of the derived category is defined correspondingly. So again, we take as points the indecomposable pure injectives in the derived category, and as closed sets, again, the indecomposable pure injectives in definable subcategories. Okay, so these are topological spaces. And yeah, that was what I wanted to tell you about the Ziegler spectrum. And now let's move on, and I'll define what a Kosilting complex is. First, some notation. So we are looking at two-term Kosilting complexes. So we are now focusing on the following complexes, which I denote in this way. So these are complexes in the derived category that are concentrated, complexes of injectives that are concentrated in 2 degrees, in degree conventionally degree 0 and 1. So they are quasi-isomorphic to complexes of this form, I0, I1, and all the rest is 0. And these are injectives. And then we will denote, I will denote by the Ziegler spectrum 0, 1 of dA will be just the pure injective, indecomposable pure injectives in this, that have this form. So it's K01 in A intersected with the Ziegler spectrum of dA. Okay, and now we say that an object complex sigma in this K01 dA, no, in J, sorry. I hope I have written in J here. Yeah. This is a two-term Kosilting complex if it satisfies 2 conditions. First of all, it has no self-extensions, so Hom in the derived category of a product of copies of sigma from a product of copies of sigma to the shift of sigma has to be 0 for any set I. And of course, also there are also the homes to higher shifts will vanish because it's a two-term complex. And secondly, we want, so this is a sort of, the first condition is as I said, is a strong form of the non-existence of self-extensions. And the second condition is a condition on generation. So it says that the category of all bounded complexes of injectives can be obtained from sigma by taking first the product closure of sigma and then closing it up under shifts and extensions. So let me explain what I mean by this prod sigma. This is a notation I will use also later. I denote closure under direct products, direct summands, and isomorphic images. And when I write tria, I'm taking the smallest triangulated subcategory containing this. So I'm closing under shifts and extensions. Okay, so this is my definition of a Kosilting complex, and it's what is it? It's the dual of a silting complex upgraded and removing compactness, so allowing for arbitrary injectives. Okay, now we say that I was introducing before in the theorem some equivalence. So we say that two Kosilting complexes are equivalent to Kosilting complexes sigma and sigma prime are equivalent if they have the same product closure. So they coincide up to taking products and direct summands. Yeah, so now let me collect some facts. On Kosilting complexes. So the first observation, I have already said this, is that sigma is always a pure injective object in the derived category. So is pure injective. And this goes back to an old result by Bazzoni, who showed that cotilting modules are pure injective in the module category. And then this has been adapted and transferred to complexes. And so I should quote Bazzoni and Marx Stovicek. Sorry, Marx Vittorio. Okay, so that's the first point. And then, so now we can look at the following set. We take the product closure of sigma and look at the indecomposable pure injectives in the derived category. So, of course, all objects of prod sigma are pure injective. So what I'm doing here, I'm taking the indecomposable objects in prod sigma. And this turns out to be a closed set in the Ziegler spectrum. this uses, I mean, this is not so easy to show. It uses properties of the Ziegler spectrum and property of co-silting theory and combines them. And then as a consequence of this, we also get a closed set in the Ziegler spectrum of the module category by taking the zero cohomologies of N and taking indecomposable objects there. So this is a closed set in the Ziegler spectrum of the module category. Okay, so moreover, we know, I mean, this is easy to observe that N, first of all, N is contained in this, it consists of two-term complexes of injectives, so it's contained in what we have denoted in this way. And inside here, it is a rigid set, and it is a maximal rigid set. Let me explain what I mean. Is a rigid set. That means that if you take two complexes in N, mu, and the second is shifted by 1, then this is always 0 for all mu and mu in N. And it is maximal with this property. So, and it is maximal among all rigid sets. In this collection of complexes, of pure injective complexes of two-term complexes of injectives. Okay, so next fact, using the closure property, so using that this is a closed set, one can prove that prod of N, so if I take direct summands of direct products of objects in N, what I get is prod sigma. And this is what I meant before when I said that despite the fact that a pure injective is not, that a co-silting complex has not an indecomposable decomposition, its equivalence class, if you are interested in the equivalence class, then it's the same as taking products of indecomposable objects. So the indecomposable objects here, they determine already the equivalence class. And so it means that we can reduce many questions to indecomposable objects. Yeah, and then now in particular, it means that we get an equivalent co-silting complex by taking just a product of objects in N. If we take the product of all objects in N, then this will be a co-silting complex and it will be equivalent to sigma because the prods are the same. So we can assume without loss of generality that sigma is just a product of indecomposables. And then we can go on, because if you think of a two-term complex of injectives as a complex, you can always write it as a sum of three kinds of objects, namely, one, the minimal injective copresentation of the zero cohomology. Then you will have a summand which is just given by an isomorphism between two injectives. And then you will have a last summand which has the form 0i, 0 to some injective. So in every complex, two-term complex of injectives can be decomposed in this way. And now if your complex is indecomposable, then it is of one of these kinds. Either it's the minimal copresentation of some module, minimal injective copresentation of some module, or it has the form 0i. So it's a shifted injective. because the other summand, the one that was given by some isomorphism between injectives, becomes 0 in the derived category. So that means with this observation, it means that we can make a further reduction and take as, so let me first introduce a notation. We write I for the set of injectives which have no morphisms from Z. Recall what Z was. Z was the set of 0 cohomologies of objects in N. So here we are taking this set of injectives, and then we can look at the following complex, which is given by the minimal injective co-presentations of objects in Z, so 0 cohomologies of objects in N, plus, sorry, and this is not a coproduct, this is a product. And here I take the coproduct of these complexes 0I with I in I. So, and I'm claiming that this, so I should explain what this mu m is. So this is a minimal injective representation of N. So what I have done here, so I mean, I was saying we can replace sigma by the product of the complexes in N. And now we have discussed that every complex in N either is either is of this form or is of this form. So I have taken all those that have this form. The mu m's with M a 0 cohomology of something in N, and the complex is 0I, and because, as we have seen, N is a rigid set, the fact that this and this have no extensions with each other is reflected in this condition. So that is what happens if you take the product of complexes in N, then you get, in fact, something of this kind. Okay, so, and this, as we have discussed, is a Kosiltin complex. Equivalent to sigma. Okay, so now you can already imagine what happens, because now what we have seen is that the equivalence class of sigma is determined by two sets, this set Z and the set I. And this will give our Kosiltin pair. So let me write down the definition. Definition: a pair Zi with Z, a subset of the Ziegler spectrum of I, and I, a set of indecomposable injectives, is a rigid pair if first condition is that the minimal injective co-presentations of the modules in Z form a rigid set. And second condition is that Hom Zi is 0. which is the same as saying that the mu-m's together with these complexes 0I form a rigid set. Okay, so this is a rigid pair, and now a maximal rigid pair is called a co-silting pair. And when I say maximal, I mean with respect to the order which is given by comparing both components. So Zi is less than equal than Z prime I prime is Z if Z is contained in Z prime and I is contained in I prime. Maximality is with respect to this order. Yeah, so now we can look at the bijections that I was stating before. So back to the first statement in the theorem. Yeah, so we have seen that two-term co-silting complexes if we take their equivalence classes, then we have seen that sigma is equivalent to a complex of the form sigma Zi, and then to this we can assign the pair Zi, which is a co-silting pair, according to the definition I have just given. So this will give a bijection between two-term co-silting complexes and co-silting pairs. And so I hope I could convince you that it is well defined, because sigma is equivalent to such a complex, and then I have a corresponding co-silting pair. And in the other direction, if I start with a co-silting pair, what can I do? I can form, given a co-silting pair, I can form this complex, sigma Zi, just by taking these guys. And this complex it's formed by taking a rigid set of complexes. And so we can use Boncard's completion to show that it will be a direct summand of some co-silting complex. But because I have also asked this maximality, it will be itself a co-silting complex. That's more or less the idea how to go back. And so we have this first bijection between equivalence classes of co-silting complexes and co-silting pairs. And now the theorem was also connecting with torsion pairs, with the lattice of torsion pairs. And now we can proceed. I mean, we know already, this was already known, that the equivalence classes of two-term co-silting complexes are in bijection with the lattice tors A. This is a consequence of results, a combination of results of a result of Crowley-Bouvi together with results of Wei-Zhang and Breas-Jemlitska. But here I would like to give you directly a bijection with co-silting pairs. So let me write down this. So tors A, we have a bijection between tors A and co-silting pairs. Which goes as follows. You start with a co-silting pair TF, and you assign to it the pair Zi, where in fact I have only to tell you who Z is, because I is then determined by Z. And what is Z? I are just the injectives that are homoorthogonal to Z, so they are determined by Z. And Z, how do I construct it? I take the X injectives in a torsion-free class, which is formed by taking the direct limit closure of the torsion-free class we started with. And of course, I take only the indecomposable pure injectives there. So, and what does it mean to be X injective? It means, first of all, to be in this limit closure, to be in this torsion-free class, and then to be X orthogonal to any object in this torsion-free class. Okay, so that's how to pass from a torsion pair to a cosilting pair. And conversely, if you have a cosilting pair, Zi, then you assign to it the torsion pair TF, which is formed as follows. So where T is the homoorthogonal of Z, and by this I mean the modules in mod A which have no homs, two modules in Z, and F are the modules which are co-generated by Z, the finite dimensional modules which are co-generated by Z, so which are submodules of products of modules from Z. In this way, so it is, you take, what we are taking is the torsion pair co-generated by this set Z, and we are restricting it to the finite dimensional modules. That's the image of Zi. Okay, so this was the first statement of the theorem. Now I turn to the second statement. So about the second statement. So I need to introduce some terminology. First of all, I will say that a module, so we will look at the modules that occur in the class, in the set Z of a cosilting pair. And they are, say, the large version of tau minus rigid modules in the following sense. So we say that a module M in mod A, we call them strongly rigid, if M occurs in one of these sets Z. So is in Z for some cosilting pair Zi. So in particular, it is an indecomposable pure injective module and occurs in a cosilting pair. And equivalently, let me give an intrinsic description. Equivalently, this means that mu M, the minimal injective copresentation, it forms a rigid set. Okay, so these are the strongly rigid modules. And as I said, they are the analog of the tau minus rigid modules in the large setup. But if you know the papers, I think this is shown in the paper of de Monet, this many authors paper, de Monet, Yama, Wright and Redding, Thomas, they show there that if you have a finite dimensional, if you have an indecomposable tau minus, they show the dual effect. If you have an indecomposable tau minus rigid module, then and you take the corresponding, so the category of all sub-objects of these modules, then this gives rise to a torsion pair, but to a special one, to one which is completely join irreducible. And in general, if you work in the large setup, this is not automatic. So you have to ask for this. And so let me first, and of course, now we are working on the dual side, so we want completely meet irreducible. So let me recall what this means. If we have a torsion pair, and we say that F is completely join irreducible. Sorry, meet, I wanted to say meet. If it can't be written as a meet of strictly larger torsion classes, so that means that whenever, if for any, and we will abbreviate this by CMI, if for any family of torsion classes Ti such that T is the meet, so the intersection of the Ti's, we have that T equals one of these classes. They can't be all strictly larger. Okay, and why are we interested in the completely meet irreducible torsion pairs? Because we have the following fact, which is proved by Barnard, Carroll, and Ju, that says that there is a bijection between the collection of all bricks and the torsion pairs in tors A with T being completely meet irreducible. And this bijection is given by taking a brick and mapping it to the torsion pair co-generated by this brick. So I will abbreviate this by TBFB, and it is the torsion pair where the torsion class is given by the modules that don't have maps to B, and the torsion-free class is the smallest torsion-free class containing B. Okay, so we have this bijection, and now we can look at the cosilting. So now we have a small torsion pair in tors A, and we know it is associated to some cosilting pair. So let's look at the associated cosilting pair. Consider the cosilting pair Zi associated to this torsion pair. And one can show two things. First of all, that there is a unique module in Z such that Bm is non-zero. And in fact, this non-zero homomorphism, there is a monomorphism from B to M, and using this, one can show that the torsion class TB is the Hom orthogonal of M. So to have no maps to B is the same as having no maps to M. And so now I can finally explain what this strange notation rigid CMI of A was, because now this module M that we get here, it is contained in a Kosilting set, so it is a strongly rigid module, and it has the condition, it has the property that this torsion-free class coincides with TB, so it is completely media-reducible. So now I denote by this rigid CMI of A, I'm denoting all the strongly rigid, the collection of strongly rigid modules M, such that this torsion class, the torsion class co-generated by M, is completely media-irreducible. And as usual, I'm taking isoclasses. And now I can state the bijection. So the bijection goes from the collection of all bricks to this collection of strongly rigid modules, and takes B and maps it to this module M associated with B, as we have seen before. And conversely, the opposite, the inverse map, takes M and maps it to a reject, namely to the intersection of, so I would denote by E the endomorphism ring of M. And here I'm taking the reject of the radical. So I'm taking the intersection of all kernels of maps in the radical of E. And notice that when M is finitely generated, this is nothing but the socle. This is precisely the socle of M over the endosocle, the socle of M over its endomorphism ring. So this shows that this is precisely the restriction, or no, the extension of the bijection, of the dual bijection we saw before, the bijection of the Monet-Yamahasso. The bijection of the Monet-Yamahasso sends a module to its top, and the dual bijection sends a module to its socle, and that's exactly what is happening here when the module is finitely generated, and that's the natural extension to the large setup. Okay, and I should point out that this construction of the reject is also studied by Ali Reza, Nasr Isfahani, and by Ramin Ebrahimi in a more general setup. And yeah, so there is some parallel work of going on in Isfahan, in fact. Okay, so thank you very much for your attention, and I'm closing here.
So thank you very much for your very nice talk. Are there any questions or comments? Yes, please.
In the first bijection of the first, in the first theorem, in the section of the bijections, you mentioned that for going back from co-silting pairs to two-term silting complexes, we make use of Bongard's completion.
Mhm.
So my question is, how well behaved are co-silting pairs in terms of mutations?
Yeah, thank you for this question. I forgot I forgot to say that in fact these co-silting pairs, I mean the work I'm presenting here is the first part of a larger project together with Francesco and Rosie. And the original motivation of looking at these co-silting pairs was to have a way to describe mutation, because in work, again with Rosie and with Jan Stovicek and with George Vitoria, we have introduced a notion of mutation for co-silting complexes. And if we look at this operation of mutation for two-term co-silting complexes, then this can be translated into an operation of co-silting pairs. And I had no time to discuss this now, but yeah, and it is well behaved, and you can describe explicitly what the mutation of a co-silting pair is. It's a bit technical, it's a bit complicated to phrase, but there is an explicit rule how to mutate.
Thank you. And a follow-up question, if I may. When taking the co-silting complex in bijection with a co-silting pair, are there any super decomposable direct summons?
Yeah, but you can, up to equivalence, you can get rid of them.
Okay, so intersecting with the Ziegler spectrum gets rid of the super decomposable summons?
Yeah, and we have seen that the equivalence classes don't change.
Of course. Thank you very much.
So, Lidia, there is a question on chat.
Yes.
If you can.
Maybe. How can I here? A finitely generated brick. So let S be a finitely generated brick and F of the smallest torsion-free class. Is it true that S is the only thank you for this question. I don't know. Okay, it's certainly the only, so it's certainly the only torsion-free almost torsion in F of S. But I don't know when we take the limit closure. Yeah, that's a problem we have faced. I know this problem.
Because in our work also, we have such problems, and it seems difficult.
It seems, yeah, I believe that this is difficult. Yes, yes, yeah.
Sorry. May I also?
Although, just a moment, maybe I'm misunderstanding the question. You're saying, no, this should be true. So you take a finitely generated brick, and we know it is the only, yeah, but the fact, it is certainly torsion-free almost torsion there, but we don't know whether it's the only one. And yeah, that's exactly the problem. Yeah, there could be more. But for the moment, we can't say that that's the only one. Yeah.
May I ask?
Please, Jawad.
Yes. Lydia, thank you very much for your
Hi,
nice.
Jawad.
Actually, I have a nice question. I assuming in extending the theory to the large mode, you use the fact that minimal injective co-presentations also exist. Yes. Always. I mean, the fact that the injective envelope and minimal injective co-presentations.
Yes.
So does it make sense that one can think about a dual theory of co-silting, means co-silting theory in large mode using the flat modules and flat covers?
We have not thought about it, but yeah, it could be an approach, because then you don't have to bother about existence of projectives, covers, and so on. Yeah.
Yeah.
Yeah, but I have have not thought about it.
Yes.
Yeah.
Thank you very much.
Oh, there is something else in the, thank you.
You are muted, Alireza.
Oh, sorry. It seems there is no question. And thank you, Lydia, for your
Thank you very
talk.
much. And yeah. Bye bye then.